Thank you for coming to another one of our joint IIS Princeton Astrophysics Colloquia. Today, it is my great pleasure to introduce Professor Stefano Profumo from UC Santa Cruz. He is Professor of Physics at UC Santa Cruz, Deputy Director for Theory at the Santa Cruz Institute for Particle Physics, and the Associate Dean for Graduate Studies and Postdoctoral Affairs at the Faculty of Sciences. Professor Profumo earned his master's in theoretical physics from Scuola Normale Superiore in Pisa in 2001, and a PhD in particle theory from SISA in Trieste in 2004. After postdoctoral appointments in Florida State University and Caltech, he joined UC Santa Cruz in 2007. Professor Profumo's research spans a wide range of interests, including particle theory, cosmology, and high-energy astrophysics, having published over 200 articles across these three subjects. And he's also the author of the excellent textbook, An Introduction to Particle Dark Matter. I would also like to just point out that he's an avid biker, runner, and triathlete, which I discovered actually during graduate school, when after climbing a road called Page Mill Road in the Bay Area in 55 minutes and nearly dying getting to the top, I looked at the leaderboard for it and discovered that he was in the top 10, having done it in 33 minutes. So hopefully he will not be this fast during his talk. But without further ado, he will tell us about black holes as dark matter.
Thank you so much. Thank you very much. So thank you very much for having me today, a day that promises to be memorable and highly consequential. And of course, I'm talking about my talk here. Right. So I will be here until tomorrow in the afternoon, and please do contact me. Come visit me. I'm in Blue Rank Hall 125. And if you are in California, please reach out. We've got great weather and very nice people. I will talk about a lot of things today. And I will not talk also about a lot of things. So please ask me during the talk, or perhaps better afterwards, if any of those things that I will not talk about are of interest to you. There is very compelling evidence that galaxies such as our own Milky Way are embedded in large halos of dark matter. And there's also very compelling evidence that this dark matter dominates the overall matter budget of the universe to a large degree. There is also extremely compelling evidence that this dark matter is something qualitatively new, is a constituent that goes beyond what we call the standard model of particle physics. And so when we talk about a new constituent, a new elementary particle, it's worth thinking back at what an elementary particle is. Now, suppose you go on a date and you tell your date, I study elementary particles. And your date asks you, well, what is an elementary particle? And there's one way in which the date can end right there in a complete disaster. And it's if you tell the truth, as is often is the case. And the truth is that an elementary particle is an irreducible unitary representation of the Poincare group. Now, that's a mouthful, but thanks to Eugen Wigner, we know that all such representations are classified by just two numbers, the mass and the spin of the elementary particle. And so when we think about the dark matter, it's helpful to think about its mass and its spin. So what do we know about these two things? Well, first of all, we know that quantum effects should not get in the way of gravitational collapse. And what that means is that the de Broglie wavelength of the dark matter as a particle should be smaller than the smallest gravitationally collapsed objects that we observe in the sky, dwarf galaxies. And so, you know, since a dwarf galaxy is about 1 kiloparsec, and we know the velocity dispersion of a dwarf galaxies, we can put in numbers and asking our astro friends what a kiloparsec is, we can translate that into a mass scale, and that mass scale is round about 10 to the negative 22 electron volts. Now that's a very small object. So, you know, if the dark matter is that small, you got to stack a lot of them on top of one another. And so obviously you cannot do that with fermions. So if the dark matter is that light, it ought to be a boson. You know, in the case of fermions, the limits are much stronger because of Pauli's exclusion principle. Now, on the other hand, we've got limits on the dark matter mass in a completely different regime, in the ultra-heavy regime, where the dark matter may disrupt beautiful structure that we observe in the universe, structures that are very old, and that did not get tidally disrupted by a massive point-like object, which I assume is the dark matter. And so in the book that Nick was mentioning, I try to carry out this estimate, and it's not too hard to convince yourself that, again, in electron volts, the mass that corresponds to something that would tidally disrupt these objects is, you know, in the tens of solar masses, or in EV, it's 10 to the 67 electron volts. So let me draw your attention to a paper where we put this on, I think, very solid grounds, carrying out detailed n-body simulations of this type of objects. I will not get into the details. Again, ask me if you're interested in this. It's beautiful work by my former graduate student and an undergraduate student who is in Germany. Now, that's a staggeringly large landscape. It's an incredibly large landscape, which again goes from macroscopic quantum effects limits all the way to tidal effects limits. And for the longest time, in my community of folks thinking about the dark matter, we had a love affair. We had a love affair with a special place in this landscape called the electroweak scale. And it was a love affair that had a lot of reasons, of good reasons, that I'm not going to elaborate on, such as, you know, the weak interactions are the only ones that the dark matter can participate in, so maybe we have a chance to detect it. And, you know, the WIMP miracles, so the natural abundance of dark matter is explained if the dark matter has weak interactions. But as a result of this, we invested a lot of time and money and intellectual involvement, and you know, we built huge detectors whose aim was to measure the tiny energy depositions that these weakly interacting particles would deposit. But let me put this story into perspective within this landscape. And what you have is something like this, right? You're looking at a very, very thin sliver of this parameter space. Now, within this landscape, and I've been talking about elementary particles, there is actually a very important scale, which is associated with this cheerful German guy, Max Planck. And this scale is related to an interesting fact, which is that at that scale, the Schwarzschild radius of an object of mass m equals the Compton wavelength of the same object. And these two quantities are completely different in their dependence on m. The Schwarzschild radius is linear, and the Compton wavelength is inversely proportional to mass. So unavoidably, they meet at some point. And that point, if, you know, against my will, we put in constants, you realize that that is exactly the Planck scale. So what this means is that you can talk about elementary particles here on the left, but on the right, classical general relativistic effects dominate, and the quantum nature of these objects becomes unimportant. And so, interestingly, of course, if you consider the smallest possible objects in this side here of the landscape, black holes, interestingly, you get that black holes are also labeled by the same quantities as Wigner's representation theory does for elementary particles. So today, I will talk about that right-hand side of this landscape. I will talk about black holes as dark matter. And I'll take you on a journey that will start at that scale, at the Planck scale, and it will go all the way up to the upper limit that I was describing. I will talk about stellar mass objects. I'll talk about asteroid mass objects, one of my favorites. I'll talk about Everest mass, black holes. Whale mass, being from Santa Cruz, we have an attachment about whales, and somebody else here in the audience does as well. And grain of salt, dark matter. Yet the amazing thing about this story of black holes is that we can actually wrap our mind around what the mass of these objects is. And of course, the length scales are something that instead it's rather hard to imagine. These objects here have length scale of kilometers, but for instance, asteroid mass objects have a scale of a micron, which will come into play later on in my talk. So what I will not talk about is how non-stellar black holes form. Why non-stellar? Well, because for obvious reasons, stellar black holes cannot be the dark matter. We know that baryonic matter is very subdominant compared to dark matter in the universe, and stars are a tiny fraction of baryonic matter. So we need something else to produce these black holes if they are to be related to the dark matter. And there's many, many options that people have gone through over the years. Some of these options are very dear to my heart. For instance, this idea of dark star collapse to populate the so-called black hole mass gap. And most recently, we've worked on gravothermal collapse of self-interacting dark matter cores to explain evidence for very early forming supermassive black holes. And I think Michael will talk a little bit about that in the launch today. But the bottom line is you've got a lot of options to form these objects, either in the early or in the late universe. Also, each one of these formation mechanisms brings a certain distribution of black holes in mass, what we call the mass function, which is, of course, relevant when it comes to searching for these black holes. Now, the state of the art in this business looked gloomy. When I wrote my book, I dismissed primordial black holes because there were statements and there was some evidence that if you look at the black hole mass here in solar masses as a function of which fraction of the dark matter black holes can make up, back before 2019, you never got to one, right? You never got to a situation where black holes could be 100% of the dark matter. Today, the picture is very different. That is all the excluded region. The shaded regions are those where you cannot be for a variety of constraints. And since here you see now a gap, Michael, I'll tell you that what happened was the following. Here, the so-called femtolensing constraints went away because of something I'll talk about later today, which is finite size source effects. And constraints on the disruption of neutron stars in dark matter-rich environments also went away because people realized that those constraints were based on an incorrect calculation of the capture of these light black holes inside neutron stars. And so the landscape is one where there is a large swath of masses. I see your hand, just 1 second. A large swath of masses where asteroid mass black holes or light black holes can be 100% of the dark matter, and obviously I will talk about that. But there's also regions, and several regions, where primordial black holes can be a sizable fraction of the dark matter. Please. Very good. I'll be talking about that as well, and I will claim that that is another island where black holes can be the dark matter, more later. Again, ask me if you want to hear details about any of this. So let me start now with stellar mass black holes. What really drew me a few years back to look into this class of objects as dark matter candidates is the fact that I've struggled throughout my career in finding a clean signature that could be associated unequivocally to dark matter. Think about searches with gamma rays, searches with direct detection experiments, which have all sorts of nuclear physics contaminants. It's a business where it's always tricky to be 100% sure that a signal comes genuinely from the dark matter. I'm going to claim that here there is an absolute smoking gun. And this claim is based on the fact that astrophysically you cannot form black holes, at least in the standard picture, below the TOV limit. And so if you detect a merger with gravitational waves, and you're sure that this merger involves black holes, then you've scored, right? It has to be new physics. It has to be presumably something that contributes to the dark matter. If you're not sure it's a black hole merger, then by looking at even smaller masses, below what we think is the lowest mass of neutron stars, again, you have a smoking gun. And of course, there are caveats, right? You can have or you can invent all sorts of things that may fake these up as well. They all involve new physics. So that is interesting. And it's something that, again, I am thinking about, and that I know people here are also thinking about. There's ways to get around these backgrounds as well. So what we did back in the day with my graduate students was to try to calculate if a given fraction of the dark matter is in stellar mass black holes, compatibly with available constraints, and if the mass of these black holes is sort of in a Goldilocks range where it's detectable with, say, LIGO, so it's heavy enough that LIGO would be able to detect it, then at LIGO, you could actually potentially, depending on the mass function, detect several events per year. Okay, so what we did here is marginalize over the mass function. For instance, here in the largest possible event rate, this is what the mass function looks like. And I'm not going to go into the details, but the idea is that you need light guys in three-body encounters to form enough pairs of more heavy guys that then merge and produce a gravitational wave signal. So, you know, in principle, you have a lot of events, and independent of our work, LIGO, of course, went after these events. And interestingly, they've detected a few. They've detected a few. As far as I know, there's 2 candidates, maybe a third candidate that emerged recently. And let me show you what these candidates look like. So, you know, they do a posterior analysis, and they say that with 84% of the posterior, they have something that is subsolar mass. Now, of course, if you look at the label of this event, it's April 1st, so I leave it up to you as to whether it's an April Fool's joke or not. But there's more. You know, in 2020, an independent group found a different subsolar mass event with a false alarm rate of, you know, 1/5 of an event per year. So again, you have very, very weak statistical evidence. And on top of that, if you talk with the LIGO collaboration that actually did not endorse these events as subsolar mass, they would claim that they're not gravitational wave events at all. So they're just background fluctuations. But the search is ongoing. There is a hope to detect this compatibly with these objects being a subdominant component of the dark matter. So stay tuned. Now, I've claimed that asteroid mass black holes are the interesting name of the game here. And I will talk about what sort of limits our ability to go after these objects. And I will talk about what I think are interesting or promising detection strategies for this mass range. So the main way in which people look for small black holes is through microlensing. So the idea here is that you stare at a star. You'd better stare to a lot of star, and you wait until one such small object passes along the line of sight or close to the line of sight to the star. And because of gravitational lensing, you see an enhancement of the light of the star that it has a very characteristic light curve. This enhancement can be very significant, factors of 10 or so. And if you see one, then you score. The best constraints back when we started looking at this came from a 7-hour-long observation of the Andromeda Galaxy with the Hyper Supreme camera that I know Michael and others are working on. Beautiful piece of equipment that I actually know nothing about, but some of my colleagues at Santa Cruz know a lot about. And so they helped me trying to understand what was going on. And what was going on was they monitored of order 10 to the 6 stars, which to me was like mind-blowing because Andromeda is pretty darn far away. And so how they could monitor inside the galaxy 10 to the 6 distinct stars is like for a theorist. But anyways, they did. But they monitor large stars, right? A sun-like star is unfortunately too dim, even for HSC, to monitor individually. And so they were looking at much larger stars. In fact, what we did initially was to look at population models of the stars in M31, and we looked at which stars within these population models were detectable as single objects by HSC. And you see that the distribution indicates that they're much, much larger in radius than the sun. Now, that's a problem. It's a problem that even I can understand. And it's a problem because if you have a large star, this beautiful microlensing event goes away, right? Because if the star is large enough, essentially you're still getting light from the star as you get the amplification of the microlensing. And so obviously your ability to detect microlensing event is significantly decreased. Of course, that's just a simple theorist picture. In greater detail, what matters is the angular size of the object compared to the Einstein radius of the lens. And as you can see here, the magnification gets highly suppressed. And so if you take that into account and you do it radius by radius, the constraints weaken significantly. But we have this count of stars as a function of size. And so you can do the calculation in detail. And what you get is that the constraints get significantly weaker. Adding up the fact that other constraints went away, you gain an additional order of magnitude. And again, here, black holes can be 100% of the dark matter. This also tells you that microlensing ain't going to happen here. You know, that you just don't have the observational tools to look for these black holes with microlensing. Another interesting thing is that these objects actually have the same physical size as the wavelength of light that HSC is sensitive to. And so obviously, you know, from elementary physics, that you're going to get diffraction effects, which also get in the way. And so to look at objects here to the left, you need higher wavelengths, shorter wavelengths, so higher energy photons, which makes monitoring millions of sources very challenging. Okay, so there's a lot of thinking that goes into there, femtolensing, picolensing, and again, ask me if you're interested, but I will not talk about it today. Rather, I will talk about the fact that microlensing is a thing, that we've detected several stars that were microlensed with the profile that matches our theoretical expectations beautifully. Most recently, there's been a bunch of detections with the Ogle survey. But there's a problem. And the problem is, once again, as in past searches for dark matter, there's a background. There's a background that is very significant. And this background is freely floating planets, or what I prefer to call them, rogue planets. So these rogue planets are objects that, for a number of reasons, have been expelled from planetary systems early on or sort of late in the life of a planetary system, and they just float around, right? And so you may think, well, that's a small population. But that's not true. Actually, we know that Earth-sized rogue planets have a total matter content in the galaxy that is between 1 and 100 times that of bound Earth-sized planets, which is something that also blew my mind, right? You wouldn't expect that. But actually, if you look at the lifetime of an Earth-sized planet in a system that contains a Jupiter-sized planet and a star, which is, as far as we know, pretty common, you know, it's very short. It's like a few million years. And so these guys just get kicked away with three-body interactions like crazy. So there's a lot of them. There's a lot of them floating around. But the good news is that there's going to be a telescope in 2027, the Nancy Roman Space Telescope that NASA will launch in collaboration with other space agencies, which will detect many hundreds, probably thousands of microlensing events. And so that's exciting. That's exciting because it gives us an opportunity to search for black holes, which is great. But it will also detect a lot of these unbound rogue planets. So what are we going to do about it? Well, what we tried to do was the simplest possible thing, which is counting events. So you can imagine that you just study the statistics of the duration of lensing events. And of course, the duration correlates with mass. It's the Einstein radius scales like the square root of mass. As a bonus of this project, we put out a very efficient code that allows you to do this exercise with your favorite mass function and velocity distribution and spatial density distribution of your lenses, called lens calc pi. But the bottom line is this. The bottom line is that if you look at the duration of events and you take into account the cadence of Roman's planned observations of the galactic bulge, you see that you may be unlucky or lucky, right? So in this case, statistically, you sort of see by eye that there are two populations. And for simplicity, we assumed, as it's common in many formation scenarios, that most of the black holes have the same mass. If that's true, then you can compare the expectation of freely floating planets, whose mass distribution is more or less known, not the normalization, but the mass distribution is, because, you know, ejection of planets is something you can study numerically and even analytically. And so in this case, it's pretty clear that you have statistical arguments that may distinguish two populations. In that case, it's not. And so you can put this sort of in a plot where, as a function of the FFP abundance, and this I'm normalizing to the mass of Earth-sized objects compared to that in bound planets. And you can see that Roman will have a great sensitivity that will far exceed current constraints, that will probe the ogle events as originating from rogue planets versus primordial black holes. Unfortunately, because primarily of the cadence of Roman, there's no sensitivity where black holes are 100% of the dark matter. But the good news is that my former postdoc, who's now at University of Maryland, Will DeRocco, has become such an expert on this stuff that he's actually part of the Roman collaboration and lobbying really hard that they change their survey strategy. Because, you know, obviously you can do better than this, right? You can look where there's more dark matter and less freely floating planets. You can have follow-up observations and many ways in which you can beat these type of constraints. Michael, I see your hand. Correct. Correct. So we have accounted for that population as well in our histograms. Again, there's ways in which perhaps you can control that population, which I would argue is perhaps much better known than these rogue planets, especially when it comes to the normalization. So that's exciting, but also frustrating, because this asteroid mass window will remain largely unconstrained. So, you know, when you hear talk about asteroid mass black holes, there usually is the claim that they sort of unavoidably produce a background of gravitational waves, mostly from isocurvature perturbations. That's not generic, right? You can come up with many scenarios where that's not true. Of course, as I mentioned, you can use higher frequency light, but that is also tricky. That is also tricky primarily, again, for similar issues to the finite size source effects that I mentioned. So something that I've been very, very interested in, and that Michael, if you'll allow me, I'll talk also about at the lunch today, is perhaps we can look for the same stuff that LIGO is looking at. So mergers of black holes, the in-spiral phase and gravitational wave emission from black holes. Now, the problem is that, as you may know, the frequency at which a binary merger emits correlates with the inverse mass of the black holes that merge. And so LIGO is sensitive to Hertz frequencies and is sensitive to solar mass objects. If you want to look at 10 to the negative 9 solar masses, you're going to get gigahertz frequencies, right? And so that's kind of an issue, because we don't really have gigahertz gravitational wave detectors. Or maybe we do. Or maybe we do. Because something that is known as the Gerstenstein effect, essentially the graviton couples in very similar ways, slightly different, to the axion to the electromagnetic field. And that's a simple calculation that even I can wrap my mind around. You just do, a linear expansion in GR of the action to first order when you put, your G mu nu as eta mu nu plus H times F mu nu, F mu nu. And you come up with a term that couples gravitons to the electromagnetic field. Now, it's different from the axion coupling, obviously, because we're talking about spin 2 particles versus spin 0. But there is a coupling. And interestingly, this is the reason why axial search experiments, and namely resonant cavities like ADMX that operate at gigahertz frequencies, actually are sensitive to gravitational waves. And for the longest time, people were like, well, yeah, that's true, but the sensitivity of ADMX is insufficient to detect a signal. And in a recent paper, we've shown that that's not true, actually. That in principle, if you're very, very optimistic, you can actually detect at significant rates, at least, with ADMX next generation, but even with ADMX current generation, a few events per year. Now, that's, to me, very exciting. And as it turns out, I managed to deliver a little bit of my excitement to the ADMX collaboration. And so we're actually working together to look for these transient events. Notice that ADMX does not do any transient search for signals because that, axions don't behave like this. Axions produce a steady signal. And so, they're sitting on a bunch of data, decades of data, and they've never looked for blips that would look like, a LIGO merger event. And so we're doing that right now, which I think is, independent of this, a very interesting exercise. And again, Michael, I'll be happy to talk about this at lunch. So black holes explode. Black holes expire. And the reason is quite simple. The reason is that if you put quantum field theory in the background of a black hole metric, an asymptotic observer seeing the same thing as a quantum field theory in a thermal state with a temperature that is inversely proportional to the mass of the black hole. And so if you go back to your intro physics, as some of you have learned at UCSC, you realize that black holes shed mass exactly or very similarly to a black body, meaning that they emit proportionally to their surface area and the fourth power of temperature. But the surface area, of course, is proportional to the Schwarzschild radius, which in turn is proportional to mass. The temperature is inversely proportional to mass. So black holes shed mass as the inverse squared of their mass, okay? And so, even I can integrate the differential equation. And what the differential equation tells you is that the lifetime of black holes is proportional to the third power of its mass. And so at some point, black holes expire. They evaporate. They produce all sorts of stuff, as black bodies do. And in particular, if their mass is about 5 times 10 to the 14 grams, which again is a mass I can wrap my mind around. Their temperature is in the hundreds of MeV, which is painful, as I'll explain, because that's a QCD phase transition type temperature. They are exploding today. So the beautiful thing about black hole explosions is that, unlike supernovae, they have a universal light curve that is exactly the same for all black holes of a given spin and charge, right? That you have small modifications if the black hole starts off with some spin and charge, but it's very minor, okay? So they're perfect standard candles. And what they look like is essentially backwards gamma ray bursts. So they have an afterglow and then a runaway process that depends on this 1/m squared emission rate. And after that, there's nothing. And after that, everything disappears. I've toyed with the idea that maybe evaporation products thermalize in a chromosphere or in a photosphere, but that actually does not happen for interesting technical reasons that I'm happy to go into. So notice that there are two curves in this diagram, and there are two curves because if the standard model is not the whole story, at some point, you may start emit when the temperature of the black hole equals some new degrees of freedom mass, you can actually emit these additional degrees of freedom. And so as a result, the evaporation rate increases because you have more stuff to produce. And the black hole light curve changes a little bit. And you can actually use that to constrain the number of completely secluded, in principle, additional degrees of freedom, right? So if you have, for instance, 100 degrees of freedom, your light curve at a high-energy gamma-ray telescope like Hawk would look completely different, right? So that's interesting because, in principle, you have a handle on the number of dark degrees of freedom that is completely independent of how these new degrees of freedom couple to the visible sector. And I think that's really cool. And we're trying to understand what this means in depth, actually, with an undergraduate student. Problem is not too hard. The problem is devising how you can best constrain this thing. Notice that the remaining lifetime here is very short. Right? We're talking about a fraction of a second. And so what that means is that this object has to be very, very close, which may or may not be the case. Okay. Again, if you're curious about this, please do ask. So how can we search for these admittedly really cool events in the sky? So what matters is at which point the black hole is in its evaporation process and how far it is, right? That's the name of the game, how far it is and how hot it is. So the remaining lifetime scales very quickly with the mass of the black hole. So if the black hole is a ton when we start our observation, then we only have a fraction of a second. But when we start observing it, the black hole is like 100 tons, then you actually have 5 days of leeway, so that's a little more reasonable. And then the age of the universe is just a few orders of magnitude farther away. So objects that are more massive than this are still evaporating, so we can still go after them and maybe detect them. So the temperature is also very relevant because, you know, as black bodies or quasi-black bodies, black holes will preferentially emit in a certain energy range. And so you should use telescopes that are very different, right, from very high energy to sort of, you know, gamma ray burst monitors or so. And so I'm not going to go into the details of this plot, but you can use, you know, the prospect sensitivity of things like the Cherenkov telescope array, Veritas, the Chinese telescope LASSO, and so on, all the way to the LAT, to calculate which distance these objects have to be as a function of their mass. And everything that is below these curves, that is close enough, you can actually detect. And notice that given current constraints, these guys can be there. Okay? These guys can, in principle, be there. Again, I'm not going to go into the shape of these curves, but they're perfectly understandable in terms of what happens to the evaporation process. Now, these dashed lines are something that is quite interesting. These objects are so close. In fact, this is 1 astronomical unit. These objects are really close, if we are to detect them, that if the observation time is long enough, they're going to move in the sky. They're going to have some sizable proper motion. And that is a very strong discriminatory feature of these events, right? We're talking about angular scales in the several degrees. So even the worst telescope has that angular resolution, even at very high energy gamma rays. So that's cool because you may claim that you've got an event, but if that event doesn't move in the sky, most likely it's not an exploding PBH. So what we did was, well, let's go look. Let's go look. And the first place we looked at is the obvious place, which is the LAT catalog of sources which are transient, whose luminosity changes as a function of time. And there's a bunch of them. And some of them have luminosity that is, maybe vaguely increase with time. And so what you can do is you can fit these light curves and try to understand what the associated evaporation event would look like. We also looked at the spectral shape of these events. Again, black holes have a universal light curve, but they also have a universal spectrum. And so you can look at that information as well. And if you put these events on the same plot that I was showing, this is what you get. Okay, you've got a bunch of candidate events that have a luminosity that changes in time in some way that you can trace back to an evaporation process. But the problem is what I was mentioning. The problem is that there's absolutely no proper motion. These sources are very steady, most likely because they're extragalactic sources, and they don't move at all, right? So what are the chances that are exactly moving along the line of sight? Very small. And so these objects, unfortunately, these events are not exploding PBH, but we have the sensitivity, we have the tools. And in fact, I think that the most promising tool is the network of gamma ray burst monitors that is operating around Earth. And here the idea is that if you have such a close by event, you can use the timing resolution of detectors that are spaced far enough, right, to determine whether an event is asymptotically far away or if it's nearby, right? Because if it's nearby, you measure significant time differences in the arrival time of the burst. And so that's actually really, really promising. And we are working with sort of the remnant of this IPN collaboration, which is one guy, he's Russian, he has other things to worry about. So it's going slowly, but we are working on it. So good. So evaporation products are detectable, and ongoing evaporation can also be used to constrain the abundance of light enough things that would not explode within the lifetime of a PhD student, but are in the process of evaporating. So now the issue is that the relevant temperatures are painfully close to the QCD phase transition. And so the calculation of the evaporation products is both very interesting and very frustrating, because the question is, how does Hawking evaporation work when you're emitting hadrons, when you're emitting bound states, which are the asymptotic states of QCD? But what happens? What are the tidal effects at the edge of a black hole that come in the way of all of this? And we try to use all of the usual suspects in trying to understand this, which was kind of cool, because these also gave us an opportunity to think about what happens if the dark matter is in the MEV, and it's sort of the sort of WIMP story, and what does MEV dark matter emit? Again, you've got hadrons coming in the way, so it's an interesting problem. And there are many ideas, I'm involved in one of them, to put up in space MEV gamma ray detectors, which is a window that we know absolutely nothing about. There were ancient NASA telescopes like Integral SPI that were launched 30 years ago, but essentially we have no idea what the MEV sky looks like. And so this is certainly a good motivation. Again, ask me if you're curious. So previous calculations were completely wrong, for a number of reasons. And we've perfected this. And when I say completely, it's orders of magnitude wrong. And we now have a code called HASMA, which apparently is a Pokemon. I didn't know. But my student was very excited about calling this thing HASMA. Anyways, this has been embedded in a code called Black Hawk, which is the state of the art in the calculation of emission products of black hole evaporation. So it's pretty cool. And you can also improve on existing constraints on the fraction of black holes. You can move a little bit your sensitivity into the asteroid mass window by using accurate calculations of the emission of black holes when their temperature is rather low. Very good. So going back to whales. All right. So whale-sized black holes are gone. If they were produced in the early universe, they're gone. They've evaporated a long time ago. But that evaporation process may have important implications for the dark matter. So we've written papers where we argued that you can actually produce dark matter from the evaporation of whale-sized black holes. You can actually produce even the baryon asymmetry in the universe from black hole evaporation in a rather natural way. And again, ask me if you're curious. You can even associate an effective operator that has to do with the Kretschmann scalar and its time derivative. If you couple the time derivative of the Kretschmann scalar to the B minus L current, naturally you have all the ingredients that you need to do baryogenesis. And if the GB minus L is in the dark sector, you actually have all the ingredients to produce an asymmetric dark matter candidate. So that's pretty cool. And we did that, again, for whale mass black holes. Also, going back to high-frequency gravitational waves, whale-sized black holes produce, in their evaporation process, high-frequency gravitons. And so they are sources of gravitational waves that are, again, detectable with gigahertz detectors if some magic happens in the early universe or if there are extra dimensions. And again, I'm happy to tell you more about this. So, last chapter of this trip, grain of salt black holes. Yes? Yes. Very good. Yes, there would be. There would be, and in fact, you can set constraints on the extragalactic background that would originate from late enough evaporating black holes. As it turns out, that actually is a little bit weaker than the constraints you can get from positron production. So positrons you produce in the galaxy out of the same sources actually give you marginally stronger constraints, but you're absolutely right that the extragalactic background is a source of very strong constraints and in principle has a very, very characteristic imprint in the spectrum of that emission. So grain of salt, right, so the Planck scale is about a grain of salt, right, in weight. And so what are we going to do about these guys? As was claimed earlier, they're probably evaporated away. They're gone. Or maybe not, right? We don't really know what happens to the Planck scale. And in fact, if evaporation stops at the Planck scale, most likely, and this is something that Page pointed out a long time ago, in fact, so long that I wasn't even born back then, that you should be stuck with some relic charge, right? You randomly evaporate into particles that carry charge. And so if evaporation at some point decides to stop, you're stuck with some charge, which obviously, being a completely random process is going to have a Gaussian distribution with an average of a few units of the elementary electric charge. So why should evaporation stop? We don't know. It may or it may not. But because maybe you have a charge, you can actually shrink the temperature of a black hole, right? Because black holes with a charge of a smaller horizon, the Schwarzschild black holes, to a point where the black hole has no temperature, so evaporation naturally stops. Or maybe there's quantum gravity that dictates that evaporation stops around the Planck scale. Either way, you may be left with a population of Planck scale relics with some relic electric charge. So these are very heavy particles that carry an electric charge, and so you can look for them. You can look for them with the same apparatus that were used to detect dark matter, because these guys certainly ionize like crazy. They kick nuclei around. So you can detect them with, say, xenon 1 ton. Actually, that's not the optimal thing you can do. You can look at them also with neutrino telescopes, like Icarus. But the best bet you have is to use ancient crystals. You can use ancient crystals because if these supermassive objects plow through a crystal, they're going to leave a very characteristic defect in the crystal. And if the crystal has been, for its lifetime, shielded from cosmic rays, and in any case, cosmic rays would leave a very different imprint in crystals because they are a lot lighter than the Planck scale. You can actually look for these imperfections and try to find or constrain the size of the population of Planck scale black holes. Now, of course, at some point you become extremal, but at the Planck scale, you can constrain a fraction of the relic black holes that carry a charge to a very, very high degree of accuracy, even if your crystal is tiny, right? Because what matters is the product of the surface area and the exposure time, right? So direct dark matter detection uses, again, a PhD student lifetime as a time scale and, yay big for the surface area. But here you have a giga-year of exposure time and a pretty small surface area. You do much better. So that's interesting. And actually what we're thinking about is what happens if black holes carry a magnetic charge. which is also a possibility, which I think is very interesting and will leave a different imprint because electric and magnetic charge do leave different imprints when they pass through matter. I'm at time, so let me summarize. I've taken you on a journey that started with stellar mass black holes that I think have a very characteristic signature in gravitational wave in the Hertz frequencies. Searches are ongoing. There may be tantalizing hints that some of these events have already been detected. Asteroid mass black holes really here are the name of the game because they can be the totality of the dark matter, but they're tricky to detect, right? Microlensing is hard. There's a significant background, which is these rogue planets. But of course, that's also very interesting for folks interested in planets. Lighter black holes evaporate, and the signature really looks a lot like GRBs, so maybe we can use GRB detectors to go after them. This would open a window, if a detection happened, on any sort of dark sector and on the size and mass scale at which dark sectors can live. And the best constraints are diffuse gamma rays or positrons. Whale mass black holes have evaporated away, but they may have left, in principle, stuff that we can detect today, such as dark matter, the baryon asymmetry, and gravitational waves. Anything else has thermalized away, and we cannot detect, but gravitational waves we can, if we are ingenious enough. Finally, grain of salt black holes may, if evaporation stops, be charged, and as such, they are detectable, most likely using paleo detectors of these ancient crystals. I will stop here. Thank you.
Questions for Stefano?
Well, I'm old enough to remember that late 70s primordial black holes were briefly popular, but once people started believing in inflation, they got a lot less popular. So are you assuming that inflation didn't happen, or you have some formation mechanism that you're assuming, or you're just saying we're going to look for them?
Thank you. So the story with inflation is the following. So if primordial black holes are very light, you know, they may actually be diluted away by inflation. That's not a problem in this story, especially. If black holes are most of the dark matter, they have to be formed later on. Roughly, the rule of thumb is that black hole masses in most formation scenarios correlate with the mass within the inverse, the Hubble horizon, right, and the Hubble horizon. And so these black holes are formed at scales much, much below where we think inflation scale is.
Formation mechanism you're assuming, or you're just assuming there's some perturbations that...
So I had a slide earlier on the large swath of formation mechanisms. Many of them historically, especially in the 70s, were related to features in inflationary potential at scales that are completely undetectable by, say, CMB or any other probes of inflation. So those models, I would say, with single field inflation are really ad hoc, okay? And so I think that's part of why people stopped taking this story seriously. And then two things happened. One is they realized there are a lot many other ways, like first order phase transitions, cosmic strings, blah, 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 where you can form these guys. And the second thing was that people realized, including my current postdoc, that if you have multi-field inflation, it's actually quite natural, almost unavoidable to produce primordial black holes with some caveats. So I would say we're fine with inflation.
You mentioned a calculation that was incorrect, that excluded some range of black holes. Is that
Neutron star capture. So the idea is, you know, you would capture within dark matter rich, say, spots in the galaxy, black holes inside a neutron star. If these guys actually lose enough energy and sink at the center, and they're massive enough, you start accreting stuff from the neutron star and you destroy the neutron star. And actually, what we did, which was really fun, was calculating what happens, how you accrete, you know, matter onto black holes when the size of the black hole, the Schwarzschild radius, is comparable to the de wavelength of neutrons inside a neutron star. So that's a cute quantum calculation. But essentially, the argument is, well, if you capture these guys, you destroy neutron stars, but you observe neutron stars, and so these guys are not around. Yes?
In terms of formation mechanisms, is there any one of these mass ranges where it doesn't require fine tuning to get the right amount of black holes to be the dark matter?
Yeah, so I always find it hard to understand what fine tuning exactly means. So I would say that if you look at models where primordial black holes form from single field inflation, then yes, I have a sharp answer to your question. But if you go beyond that, and I think it's really a good idea to go beyond that. So if you look at alternate formation scenarios than single field inflation with a bump in inflationary potential somewhere, at some field values, then, in most of this, especially in the lighter, black hole masses, we're talking about early enough times, there's absolutely no problem to come up with mechanisms to form them. Now, it's very challenging to form sort of stellar mass black holes because they form rather late in the history of the universe. And if you want to form supermassive black holes, then you really have to work hard, right? So one of my graduate students has worked on the idea that maybe you can explain the JWST, supermassive black holes with primordial black hole type formation. You can do it, but it really is a stretch. It really is a stretch. So it actually depends on where you want to form them on this mass scale.
Go ahead.
For the Everest mass black holes, you mentioned that they don't thermalize, and I was just curious, why? Why that?
So what doesn't thermalize is the evaporation products. And sort of the technical reason is that most of the stuff that evaporates in the radial direction. And so the problem, if you want to thermalize, is to get particles to talk to one another early enough. And so, unless something really interesting and peculiar happens very close to the event horizon, people have shown that the mean free path for radially propagating particles is just not long enough for them to have time to see one another and thermalize. And this holds both for QCD type interactions and for electromagnetic interactions, which is kind of a bummer because I would have loved to detect a little afterglow, but supposedly it doesn't exist. But it's an old calculation, so if you're interested in looking back at it, I think it would be a cool project. We don't really understand what happens, obviously very close to the event horizon of a black hole, and things can certainly happen that would change this picture. I think. I don't know how, but I think it is a possibility.
We have time for one more question. Nick?
Sorry,
Yeah,
go ahead, Nick.
So maybe that's a naive thought, but you have a way to convert dark matter to radiation when you evaporate these black holes. So is there any chance we can measure time-dependent energy density of dark matter in the universe?
Dependent?
Time-dependent energy density. For example, you can convert dark matter to radiation. So is it important so that we can see a drop over time in the energy density of the
Interesting. So
assume that the density is conserved.
right.
How you have a way to transform into radiation, maybe.
Yeah. So here's the thing. If black holes evaporation happens, early enough, everything thermalizes, right? If it happens and it's done by when the temperature, by recombination, essentially you have no hope, right? Everything thermalizes very quickly. But if evaporation continues, yes, you do have an energy deposition, which is significant, and it's sort of in the dark ages of the universe. So maybe you have a hope. But again, going back to what the constraints are, the best you can do is to look for diffuse gamma ray emission and especially positron emission within the galaxy. So very late production. Even if the production happens at a much slower rates than perhaps earlier on, those are the best constraints you can have. So measuring something that is redshift dependent, as far as I know, is a losing proposition compared to detecting late time evaporation.
also measure mega matter present
Yeah.
time. So
So actually right, so the best you can do is actually detecting in this mass range the consequences of accretion onto primordial black holes, which is somewhat tricky to do because these things move quite a bit. But accretion products and the resulting acceleration of particles can actually distort the CMB spectrum, give it a little bit of a chemical potential, distort the black body spectrum. And so these constraints happen when accretion is significant, which is when you have large enough black holes. So you actually have important constraints around here from CMB distortions, but not for smaller black holes. And these, again, are late time things.
All right, in the interest of time, maybe we can thank Stefano again.